Hi! The access to the sequencer in Roland MC-101, MC-707 and MV-1 via their MIDI interface has been totally undocumented. Until now. So, what can you expect from this video? I'll show you how the tone track and drum track sequencers are organized, how they store data, and how to convert sequences between the instrument's internal format and a more human-readable notation. This may be useful if you want to tweak the instrument or if you are more on the composing side of hardware music production. Once you understand how the sequencer works, you can implement things like piano roll visualizers, which I think are totally missing in these instruments. You can even build convenient converters between the MC or MV sequencers and MIDI files. If you know how to interface with the sequencer, you can even implement your own external sequence editor as a standalone computer application. Or you can try building a sequence visualizer or even an editor as an embedded device based on an industrial microcontroller. Or maybe you just enjoy your MC or MV and you are simply curious about how it works and how to push it to its limits. In this video, I'll focus on note sequencing and motion sequencing. Of course, I share all the test software for free on GitHub. It's released under a non-restrictive license, so you can freely use it as an inspiration or as a part of your own creative projects. The concepts and the software presented here were developed using MC-707. Everything applies almost exactly to the MC-101 as well, of course with the limitation of 4 tracks. I only tested the code on MV-1 briefly, but the most important concepts like sequence organization work the same way. I developed the test software under Linux, but the code is written in Python, so it should be relatively easy to port it to other platforms. It also runs on Raspberry Pi, so it is an option if you want to run it, but you don't have access to a regular Linux computer and you don't want to deal with virtual machines. The sequencer area in the address space starts at the address of 2 and 7 zeros hexadecimal. Here you can see the base addresses of all the clips and tracks in MC-707. Of course, the MC-101 will have a similar structure, except that the structures representing tracks 5 to 8 will be unused. In the case of MV-1, I checked the first 4 tracks configured as drum tracks and tone tracks, and it worked similarly. Each clip has the same structure. Let's call it a clip descriptor. A very similar structure can be found for each track, but I think not all the fields will be valid for both of these structures. So let's concentrate mainly on the clip descriptor. The clip descriptor is divided into areas for which you can get a response when scanning the address space. I didn't decode all of the fields, but just some of them, which I think can be particularly useful. Here I show you only the information I figured out, but obviously there are many more interesting settings there. At the very beginning of the clip descriptor, you can find the clip's name encoded as a series of ASCII characters. The next interesting part that I found in the clip descriptors are the settings of sound control parameters for the clip, like, for example, volume, filter, resonance, and so on. This information starts at the offset of 1 and 4 zeros hexadecimal from a clip descriptor's base address. And yes, the sound control can be set individually for each clip using the documented CC messages. But now, thanks to the Sys-Ex access, we can also read and display the initial settings for each clip. I figured out most of them, not all of them. But I think it's a matter of couple of more hex dumps, for example using the hack tools that I've already shown you in my previous video. The next area starts at the offset of 2 and 4 zeros hexadecimal from the clip base address. And I think the most interesting fields there are settings for step time and number of steps for the particular clip. And they can be quite important if you'd like to implement, for example, sequence visualizers like piano rolls. The step time is encoded as a lookup table with the values starting from 0. 0 means each step represents an 8th note. 1 means a 16th note, and so on. The step length is encoded using 2 bytes. For example, the 2 bytes 8 and 0 decode to 80 hexadecimal, which is 128 decimal. Finally, the note sequence is encoded at the offset of 3 and 4 zeros hexadecimal from the clip base address, and the motion encoding starts at the offset of 4 and 4 zeros hexadecimal. The recorded pitch bend values are encoded from the offset of 5 and 4 zeros hexadecimal. This is the part that was the hardest to figure out. But maybe don't give up and let's prepare for quite a ride. Further, I'll introduce some technical names that I use just to be able to communicate concepts clearly. But I actually have no idea how the concepts and the data structures are called officially by Roland. When analyzing the note sequencer, we can split each address into the following parts. The first 4 hexadecimal digits will represent the clip base address and the address space area for the sequence. So, in other words, the clip base address plus the offset of the note sequence area. The next 2 hexadecimal digits will represent the step index. See how the valid MIDI range of 0 to 7F nicely represents the step indices of step numbers 1 to 128. And the last 2 digits represent the parameters of the step. And this is one of the deadly parts, but stick with me. Here you can see the contents of the step number 57 encoded at the index of 56 decimal, which is 38 hexadecimal. Now let's see what's inside each step. On a hex dump, the steps don't really look very friendly, but when divided into 16-byte chunks, each step starts to make sense. At least, kinda. The step structure in a more table-like form is shown here. It may not sound encouraging for a good start, but honestly, I have no idea what's in the first 16 bytes. But moving on. At the offset of 10 hexadecimal, we have 32 bytes which contain the information about the notes playing in this step. Each pair of bytes contains a MIDI note number encoded in 4-bit pairs. So for the note C4, which has the MIDI number hex code of 3C, the corresponding pair of bytes will contain 3 and C. An empty note is a special case here, which is encoded as 2F bytes. If using unsigned interpretation, it decodes to FF or 255. Or if using the 2's complement encoding, it decodes into -1. And as you can see, each step can contain as many as 16 different notes. And here the word different is important, and we'll see later why. Next, we've got a velocity field, which is pretty obvious. Maybe except the fact that if you program the sequencer and edit the velocity in an initial step, the further steps may have the velocity encoded as when initially programmed. At the offset of 40 hexadecimal, we can see the starting points of each node within a step. The starting points are expressed in the hundredths of a step time, and they are encoded using pairs of bytes. Again, in each byte of a pair, only 4 bits are used. And there is more. since the nodes can start before a step starts, the start time can be negative, and the negative start time values are encoded in 2's complement encoding. So, for example, 0 will be 00 hexadecimal, but -1 will be FF hexadecimal, -2 will be FE hexadecimal, and so on, down to -50, which encodes to CE hexadecimal. The ending times of the nodes are at the offset of 60 hexadecimal in each step. They can have the values from 0 to 100 or 64 hexadecimal. The default values are 50 hexadecimal, which is 80 decimal. But there is a catch. If a node is longer and it ties to the next step, the end time must be set to 100, and only then the node may be continued in the next step. If the end time is set to a smaller value of up to 99, the node ends in the particular step after the number of cents expressed in this field. The last field in the node step is the information about the substep. If this field is 0, then there is no substep and the node is played once per step. But you can set it to 2 nodes per step, 3, 4 or flam. So let's analyze it in practice. Let's assume that in the simplest case, we've got a C3 node at step number 4, starting at the beginning of the step and with a default duration of 0.8 steps, which is 80 cents. The velocity is set to 123 decimal or 7B hexadecimal, and the node encodes like this. The neighboring steps remain empty. Now let's look at a more complex example. This time we also have a C3 node, but now it occupies 3 steps. It starts at the step number 6 and it's shifted 6 cents after the step starts. The node length is now set to 2.5 steps, which is equal to 250 cents. So to get the length of 250 cents, we need to tie the node in step 6 and step 7 by setting the end times in these steps to 100. And in the last step, number 8, the node will have its end time set to 56 cents because it starts 6 cents after the beginning of the step. Now let's dive even deeper. What if we have a node that starts before the start of the step? Such a node has its start time set to a negative value. So let's look at this example. Now our C3 node has again the same velocity. It belongs to step number 11, but it starts 10 cents before step 11 starts. And the length of the node will be set to 1.92 hundredths or 192 cents. So the start time in step 11 will be set to -10 and it will be encoded in 2's complement as F6, which results in the pair of bytes F and 6. End time in step 11 will be set to 100 because it ties to the next step. And in step 12, the node ends at the time of 82 cents. This way, the overall duration of the node will be 10 plus 100 plus 82. Now, let's figure out how the sequencer deals with polyphony. This part is also not so easy and not so straightforward. As you've seen just before, in any step there can be not just one node, but there are 16 nodes to be encoded, and I gave them some kind of indices like that, up to 15. And this applies to every field in each step. So to represent each step in the test software I created, I introduced the name component for each node playing in each step. Each component can be represented, for example, as a simple dictionary in Python. I used an additional field processed in the component for internal conversion procedures. And as you could see, the components are indexed from 0 to 15 in one step. So they can be represented, for example, as a list of 16 such dictionaries in Python. In this diagram, I show how we can visualize a sequence as it is encoded in the Groovebox. So here we got the grid of 128 steps indexed from 0 to 127. And in each slot of the grid, we got one component. The components are indexed from 0 to 15 and they are represented in my software as a Python list of dictionaries. And now we've got the file representation of one step. To get the file sequence, we just have to create a list of such steps. The Groovebox has the capability of storing 128 steps in each clip. The steps are actually stored in the memory, no matter if they are visible in shorter sequences or not. This way, we can represent the sequence as a two-dimensional list of components. So you can access a particular component by just writing something like this. Let's introduce the name lane for all the components of the same index. The rule here is that all the nodes must be placed as close as possible to lane 0, so to the lowest offset in each step. If we don't program any polyphony, we have the nodes only in lane 0. Let's, for example, have a node that spans from step 3 to 4, which have the indices of 2 and 3. But if you want the polyphony and you'll add another node, the next node will be placed each time as close as possible to the lowest lane number, like this. And if you add yet another and even longer node to the sequence, but let's say at step 2 of index 1, it will look, for example, like this. The sequence playback mechanism in the instrument probably tracks the node numbers between the steps and it considers the step end times if they are 100 or less. But if you program the values consistently, the sequencer will, let's say, understand the nodes. And an important thing, I noticed that if I delete a node, then the same rules apply. All the other nodes move down to the lowest lanes. Here is an example of a real pattern that I programmed. You can create the experiments using function from the file of the name shown here. You can see how the programmed nodes can be displayed in the form of a piano roll and how the nodes were distributed by MC-707 to different lanes. As long as the sequencer played single notes, they were placed in the lowest lane. But when there were more notes, they got stacked up toward higher lanes. A somewhat interesting thing here is that for the sequencer, there seems to be not much of a difference in which lane a component is placed as long as they are tightly deployed in the lowest lane numbers. Here you can see what happened when I added a node to the sequence. And here is an example of a much more complex polyphonic pattern. As you can see, it works the same, but just on the larger scale. Maybe just let me know in the comments if you are interested in how I created these diagrams. But I'm not including those video clips to keep this video relatively short. The motion sequencing in MC Grooveboxes is much simpler than the node sequencing. The motion sequencer starts at the offset of 4 and 4 zeros hexadecimal in each clip. You probably know that you can record and edit the 4 knobs C1 to C4. But there is more. You can also record the parameters like sustain pedal operation, aftertouch, module, and many more. And those parameters are also recorded independently from the C1 to C4 knobs. I tested recording of 2 additional parameters, but the MCs can record up to 4 different sources plus the pitch bend wheel separately. I didn't check that feature on MV-1 though. In the main motion sequencer, the address is divided in a similar manner as in the node sequencer, but this time we start at the offset of 4 and 40 hexadecimal in each clip. The steps are encoded like this, and the least significant byte contains the offset of the motion lanes. So this way, each step can contain up to 8 motion lanes. The lowest 4 offsets are assigned to the C1 to C4 knobs, and the latter 4 are for recording other parameters live. For example, aftertouch, mod wheel, sustain, and so on. Each step is divided into 8 sub-steps so that the motion can change with a better time resolution than just a single step time. If you program motion live or if you use the motion automation tool, the sequencer will use all the sub-steps to record and play the motion. But if you program motion using the step sequencer, the motion can be set only with the whole step resolution. All the software that I created for my experiments is available on GitHub for free with a non-restrictive license. Thanks for watching and see you maybe in the next video. Bye!